supposed to calculate the speed at the bottom. Okay, so what principle are we going to use here? What idea are we going to use to solve this problem? Conservation of energy. Okay, so we cannot use F equal ma directly because integrating the equations of motion is complicated. Okay, and this is not constant acceleration. Okay, momentum conservation won't get us anywhere, and we can say, okay, the kinetic plus potential at the initial position is equal to kinetic plus potential at the bottom for the same reason I discussed earlier. Okay, the tension doesn't do any work. Okay. And so, now, if you have, I need to get used to switching here. So this distance here is r, and this distance here, this is theta, this is r cosine theta. Okay, so this distance is r minus r cosine theta equal r minus cosine theta. So if I put my y-axis here, so here at this point we have potential mg r times 1 minus cosine theta plus 0 kinetic equal at the bottom 1/2 mv squared. Okay? Or if I have gr 1 minus cosine theta equal v squared. So this tells me, okay, that the speed, so if the angle is the same for all of the pendulums, which it is, so the speed depends on what? Only on r, which is the length of the pendulum. Okay? So the longer the pendulum, the higher it will be relative to the bottom. Okay? So the only thing we need to do here is, because we need to rank the speed, so the only thing we need to do is see which one is longer, which one is the shorter. If I go back, so number 2 is the longest one, greater than 3 equal to 4, greater than 1 equal to 5. Okay, so that's the rank. You only rank them by the lengths, with masses, no masses. Okay. And you could try to solve the problem in a way that involves the masses, okay, but eventually the masses will drop out. Okay. I'm trying to go a little faster. Okay, this is a problem that that involves this question about kinetic energy, and there are forces being applied to these objects, okay, different forces, different masses, and you need to figure out which one has the greatest change in kinetic energy. Okay, let me just as a general statement. So the definition work is force times displacement. Okay? The force multiplied times the displacement. That's the definition of work. Now then we have the work energy theorem. This tells us that the work is equal to the change in kinetic energy. So, in many problems, not necessarily this one, but so you may have a question about, say, calculating the work. Okay, so you need to decide whether you want to use just the definition and the force times displacement, or see if the problem may be easier in the sense that it may be better to just calculate the change in kinetic energy, shorter. Yeah, that will be the work. And the next problem we'll solve is one like that. Okay. So here we are asked to calculate the change in kinetic energy because you are given the initial velocity and you are given the mass. So you could calculate the initial kinetic energy. Okay, because you know the force. So you can figure out the mass, you can figure out the acceleration, you can calculate the final velocity, and then calculate the final kinetic energy, and calculate the change in kinetic energy for each of the objects. Okay, and do that lengthy calculation for each of them and figure out the solve the problem. Okay, but so using this work energy theorem, it's much easier to arrive to the answer. First of all, because the work just tells you directly the delta K, the change. Okay? Second, because you have the force and you have the displacement. Okay? Now the displacements are all the same. So what I have here is that the force times displacement of 10 meters will give me delta K. So which case will give me the biggest change in energy? So for the first case, the change in kinetic energy is 100 times 10. For the second one, 50 times 10. For the third one, 75 times 10. For the fourth one, 50 times 10, etc., etc. So I'm taking all these forces and multiplying all of them by 10. So if I need to rank that, I can just rank the forces because we're multiplying all of them by the same number. Okay? So what is the answer? Well, number 1 and number 6 are going to be the biggest change. Okay? So that's why the correct answer, delta K1 equals delta K6. Then I have the 75s, so 3 and 5, and finally I have the 50s, so 2 and 4. Okay? So the only thing you need to do here is essentially rank the forces. Problem. Okay, that will give you the answer. Let me try to jump to the next one. Okay, so here is the case where we are asked to calculate the change in kinetic energy for each interval there. Sorry, the work done for each interval. And you could figure out the force because you know the velocity. You could take the derivatives of that and calculate the acceleration, multiply times the mass that gives you the force, then figure out what is the distance it travels, and do force times displacement to get the work. That's a lot of work, and you have to repeat that for each step. But if you use the work energy theorem, you know that the work is the kinetic energy final minus the kinetic energy initial. And that's proportional to the velocity squared. So what you need to do is get v squared final minus v squared initial for each of the segments. Okay? So you have, for the first one, you go from 3 to 3. So 3 squared minus 3 squared. For the second one, 6 squared minus 3 squared. For the third one, 0 squared minus 6 squared. For the fourth one, 0 squared minus 0 squared. For the fifth one, negative 2 squared minus 0 squared, etc., etc. And then just calculate these numbers in the rank. And that will give you this particular answer that's marked here as correct. Okay? And that's very fast. So you don't need to do anything else but that. One important interesting thing here is that if you go, sorry, I'll be switching, I may interrupt, if you want me to go back to something because you're taking notes, just raise your hand. So if you have these and you go, say, from, you have 6 meters per second. If you were to go from here, say, to here, like this, okay, so probably this is a big change in velocity, okay? So now if you were to do the change in kinetic energy, delta K, this would be 1/2 m 6 meters per second squared minus 1/2 mass times negative 6 meters per second squared. And this gives you 0 because 6 squared and negative 6 squared is the same number. So you might say, oh wow, how come? So I'm changing the velocity so dramatically, it's not changing the energy, no work. And so the work is 0 going from here, so you have to apply a big force to change the velocity direction, and yet the work is 0. Okay? So that's an interesting observation, okay? And so let's see what happens. So if we have, suppose we have something going here at 6 meters per second, okay? So if we want to do this with the velocity, so reduce, so later it will be 5, then it will be 4, we need to apply a force in what direction here? If we want to slow down the 6 meters per second object, in what direction do we need to apply a force? Okay, to the left, okay? So this will be the force, okay? So then the option is to do this, and this, again, eventually some stop here, then, because the force is still going to the left, now it will stop here, and it will start moving to the left. And eventually, you will get to the same speed by going in the opposite direction. Okay? Now, if you look at the definition of work, F dot delta R, so this is the magnitude of the force, that's the magnitude of the displacement, that's the cosine of the angle between them. Okay? So in the first part of the motion, when the force is going that way and the displacement is that way, what is the sine of the work? We have the cosine of pi, okay, which is -1. So the work is negative, the first part, because the force is opposing the displacement. So the first part of the motion has negative work. But now when the thing stops and starts moving to the left, now the force and the displacement are in the same direction. And the work you do is positive. So you will do negative work all the way up until it stops, and then you do positive work. The total amount of work you do happens to be 0, cancel out. So you have completely reversed the direction of motion, but you haven't done any work. Okay. Let me switch to the easiest problem that had the lowest score in test 2.